So in the second lesson for Unit 2, Part 3, I thought it would be a good idea just to share with you the solutions that I came up with for these particular problems. So before you start watching this video, I would really highly recommend you trying these problems on your own first, and then checking in with this solution set afterwards. All right, so for question A and example number 1, let's just kind of review what's happening here. We've got a police station that's located on a straight east-west freeway, so the highway is running directly east and west only. At noon, which is when time is equal to 0, a patrol car leaves the station heading east. So if this is noon right here at time 0 and we're heading east, then I think it's reasonable to imply that a positive y value represents a position east of the patrol station, and a negative y value represents a position that's west of the station. The position function, which we don't actually have an equation for, s is equal to some function based on time. So s, as I said earlier this year, s generally stands for position in the world of physics. So S is an equation of position, and our position is based on some function, some equation that's based on the independent variable time. And that function gives the location of the car in miles east or west of the station. So again, we're saying S greater than 0 or less than 0 to indicate east or west. And to clarify things, the y-axis is now going to be considered our s-axis because s is our position, and our x-axis is going to be considered our t-axis because t is our independent variable. And if we are to describe what happens during the first 3.5 hours of the trip, well, we kind of see what's happening here. Something interesting occurs right about at 1.5. And then again at 2.0, and by interesting I mean from a calculus perspective. And then maybe right here too, there's something kind of interesting that's happening there. And so since the graph is increasing, I would say that the car moved east for the first hour and a half, then stopped for half an hour, and I know that it stopped because its position did not increase or decrease on the s-axis. So there was not moving further east or further west at this point, and we assume that he stayed on the highway, or she stayed on the highway. So the car stopped for half an hour and then started heading towards the west. Because the s value is decreasing now, our distance from the police station is decreasing. That must mean that we're heading back west. And then at this point here, can you tell what happened? Well, we must have passed the station because there our distance east from the station is back to 0. And if the distance is back to 0, well then we're right outside of that station. But the police officer did continue past, and we don't really know what happens after that. So I'm going to switch to my green pen now and start talking about question B. Calculate the average velocity of the car between noon and 2 p.m. So noon was time 0, so 2 p.m. must be the number 2. And let's just remind ourselves here, average velocity is a rate of change. So that's simply the slope between these 2 points. And we've got this coordinate here, 0, 0. And at time 2, we've got the coordinate 2, 80. And so if we find the slope of that line, then we have found our average velocity, or our average rate of change. And so we've got units, let's be mindful of, 80 minus 0 miles divided by 2 minus 0 hours. So on average, for that 2-hour stretch, the police officer was traveling at 40 miles per hour. Now hopefully you recognize and can understand instantaneous velocity, and you'll recognize that especially through this stretch right here, the steepness of the actual curve is greater than the steepness of the average rate of change. So you know the cop was traveling faster than 40 miles an hour for this stretch, and then again for this stretch here, but at this point when the steepness is a little bit less, that's what kind of averages it out to 40 miles per hour overall. For part C, I'll switch to my blue pen here, calculate the displacement. Actually, let me clarify this here. This was slope. And then displacement, if you haven't seen or heard that phrase before, this is essentially, in this case, the distance traveled. So calculate the distance that's been traveled and the average velocity of the car between 2 and 3:30. So between a time of 2 and 3.5. Oops, and I just realized something here. I wrote down the correct data point, but I located it in the wrong spot. So let me fix that here with my green ink. I don't think our math was incorrect at all, but my picture sure was. So this was the coordinate 280, and we're using that coordinate again, 2, 80 for question part C, and we're going to 3.5. Now the x value is 3.5, but the y value, I should say the t value and the s value, the y value is down here at -20. So we've got the coordinate 3.5, -20. Now again, for average velocity, we just did that a minute ago, so we know that that's going to represent our slope. And let's just remind ourselves of something here. Slope is the change in s, in this case, divided by the change in t. So delta s divided by delta t. But it's this delta s that represents our displacement. This is the distance traveled, right? So the distance that we've traveled, well, we were 80 miles from the police station, 80 miles east from the police station. We ended up 20 miles west of the police station. So as far as our displacement goes, we'll just subtract the y values, or the s values in this case. And it doesn't matter which order you subtract in, as long as you retain your sign. So we have -20 as our y2 value, if you will, minus 80, our y1 value, and it looks like we ended up with a result of -100 miles. Now displacement doesn't really need a negative sign here, but I do like to include it because let's understand what this means. A negative number in terms of this s-axis, or the y-axis, means that we were heading eastward for 100 miles. And so that's just helpful to know, perhaps in the grand scheme of things. So as far as our average velocity goes, well, we've traveled a total of 100 miles westward, and we did that in an hour and a half. So the average speed was 66.6 repeating miles per hour, and because of the negative sign, we know that we were traveling in the direction west. So we actually have a velocity and not just speed. And so revisiting this notion of instantaneous velocity, at what time is the instantaneous velocity the greatest as the car travels east? Well, in order for it to be traveling east, then it's got to be sloping upward. Down here, it's traveling westward, so we're not really interested in this westward movement. But eastward here, the instantaneous velocity is the steepest, where the curve slope, the slope of the curve, is the greatest. And it's a little bit hard to tell because it kind of appears to be flattening out right here. But we're increasing speed, of course, from a stop, and then we're decreasing our rate of speed as we approach a stop here as well. So the maximum speed, I think the steepest point is right about here. And if we could imagine the steepness of this tangent line, that would represent our instantaneous velocity at its greatest. And so again, I'm just notifying that eastbound is some sort of positive slope at the tangent line, and I would argue that the highest instantaneous velocity occurs between 30 and 60 minutes after start, or somewhere between 0.5 and 1 on the t-axis. It might very well be right here in the center. It's just a little bit hard to verify that, since we don't have an equation to actually perform the math. And for part E, we already kind of answered that. When is the patrol car at rest? Well, the car is stopped or at rest on the t values from 1.5 to 2. And we can say that the velocity is 0 because the displacement is not changing. And so as we start to look at question number 45, we're going to turn our attention to a slightly different equation. This is x of t. The function is built on t as our independent variable, and x is actually the dependent variable. We see this from time to time, especially in physics classes, when a position x or y is based on some movement relative to time. So don't be surprised if we see these again. But what's happening is we've got this object, this block of wood as the picture kind of describes it. It's hanging on a spring and it's at rest. So you can imagine if this thing's hanging on a spring and it's at rest, it's just hanging there still. If we pull the mass 10 inches below its point of rest, and then as we release it, we give it a little bit of an upward push, then the distance in inches of the mass from its equilibrium, from this midline position, after t seconds is given by this function, x of t. When x becomes positive, the mass is, of course, above the equilibrium point, and when x is negative, then it's below. And so I graphed that with my TI calculator, and here's a screenshot from the TI calculator. I would recommend that you try practicing it there too, since you'll be able to use those calculators on your upcoming test in a couple weeks. If you use Desmos or some other graphing tool, that's fine to practice with. Just remember that on the tests you won't have access to any internet-based graphing tools. And if we had the ability to zoom way in here, you'll notice that the height is at -10. It's really kind of hard to tell, but about -10 is right here, right on the vertical axis. And the TI doesn't allow me to change the variables, but we should really recognize this here, that this is a t-axis and an x-axis, where x is position and t is time. So as time moves forward, we're seeing this position kind of oscillate. The spring is doing its thing and the object is bouncing up and down. So that's exactly what's happening in this graph, and it does kind of represent what's happening in real life. Now, while the function is x of t equals 10 sine t minus 10 cosine t, its derivative is pretty straightforward. 10 times the derivative of sine, which is cosine, 10 times the derivative of cosine, which is negative sine. And when we combine those two, 10 cosine t plus 10 sine t, that is our derivative of x with respect to t. Now, I added a little note here that v is equal to, and I did that deliberately because v stands for velocity. We could have started this equation with s equals, s is our position, and the derivative of position becomes velocity. And so that kind of helps us describe what's happening in part B. This equation, although it looks real similar to the first equation, describes the velocity of this object that's bouncing on this spring. And if we wanted to know when the object wasn't moving, we would simply set this velocity equation equal to 0. And we would find when does velocity equal 0. And so I've got 0 equals 10 cosine plus 10 sine. And there are a variety of ways that we could solve that. What I ended up doing was I moved the 10 sine t to the left, divided both sides by 10, and I had to determine when does the opposite of sine equal cosine. And the way I solved that is I thought of our unit circle. So within a unit circle, when are sine and cosine opposites of one another? Well, they're equal to each other right here and here, right? Because the x-coordinate in this case is radical 2 over 2, and the y-coordinate is also radical 2 over 2. And over here, they're just opposites of that. So these two green positions are out. But where they're opposites of one another are here and here, where we've got a negative radical 2 over 2 and a positive radical 2 over 2. So sine is opposite of cosine here, and same thing down here, radical 2 over 2 and negative radical 2 over 2. So again, sine and cosine are opposite in that position. So this angle is 3 pi over 4. This angle is 7 pi over 4. And if we were to continue rotating around this unit circle, well, we'd see an infinite number of positions, or, and in this case, time. After 3 pi over 4 seconds, the object is technically not moving for that split second. Then again, at 7 pi over 4 seconds, 11 pi over 4 seconds, and so on. I didn't spend a whole lot of time answering part D, but what came to my mind is that this would be unrealistic because the movement of that spring doesn't seem to be dampening at all. If you were to release this spring and let this, or release this object that's hanging on the spring, eventually it would settle to equilibrium again, but it doesn't look like that's happening here. The position function remains constant without end, and so does the velocity function. It doesn't ever end or tend towards zero. There may be other reasons why this is unrealistic, but that's the first one that I came up with. So that's what I've got listed here. So in question number 49, we've got a cylindrical tank that's full at time 0. When the valve in the bottom of the tank is opened by Torricelli's law, the volume of the water is represented by this particular function. So I used the Desmos calculator to graph this function, and that's it down here. And the question in part A says, well, how much is in this tank at time 0? That's easy to investigate. If we substitute 0 in for x, we've got 100 times 200 squared. 200 squared is 40,000, and 40,000 times 100 is 4 million cubic meters of water. That's a gigantic tank. That is very, very large. And I just did a quick calculation off to the side here. These swimming pools are what we're talking about here. These round pools, or is what I'm thinking of here for a second. If you took a 30-foot round swimming pool, 30 foot's pretty big. I did the calculations real quick here, and I think a 30-foot diameter round pool only contains 82 cubic meters of water. So if that swimming pool contains 82 cubic meters, and this tank contains 4 million cubic meters, sorry, my units were wrong here, cubic meters, you can imagine how large this tank is compared to just a single swimming pool. So in part B, when we're asked how long does it take for the tank to empty, well, that's pretty straightforward. We want to know when the volume is equal to 0, so we'll set this original function to 0. We can technically divide both sides by 100, take the square root of both sides, and now 200 minus t equals 0. T itself has to be 200 hours, which is about 8 1/3 days. For part C, find the rate at which the water flows from the tank and plot the flow rate function. Well, again, the flow rate is the derivative of the volume function. So this V does not stand for velocity in this case. This V stands for volume. And the change in volume with respect to time, the dV dt, would be a good use, or this would be a good use of our chain rule. So 100 is our constant multiplier. We'll leave that alone. But the derivative of 200 minus t squared, bring the 2 down front, multiply that by the inner function untouched, and then multiply by the derivative of the inner function. This would be a good opportunity for us to clean the math up with some algebra. We ultimately end up with the function 200t minus 40,000. And we can graph that. Now this particular function is defined for x values or t values less than 0 and greater than 200, but we're not really interested in those because we know at time 0 the valve is open, the drain valve is open, and at time 200 the tank is empty. So the fastest rate of flow can be confirmed 2 ways. Number one, it's the quote largest value on the derivative graph, and I'm saying largest because it's the farthest from 0. So that's where the water is flowing the fastest, and that position also correlates well with the original graph because back here at time 0, this is where the tangent line was the steepest. Any other point of tangency along this graph is going to have a less and less steep slope. When we get down to the bottom, we have a slope of 0 because the water is no longer draining. So we have the smallest slope or the slowest rate of flow right here at the minimum point or at the derivative value that's equal to 0. And so if we were to describe that in words, we can answer that like I did here in part D. The water flows the fastest the moment the valve opens, and the rate slows until the tank is empty. And I would assume that this is because the weight of the water above the valve is reducing. With less mass or less weight to the water, it doesn't have to evacuate as fast. So this example here, example number 3, is a really good description and understanding how position, velocity, and acceleration relate to one another. This equation, of course, is established in an ideal world where friction has no effect on it. But according to Newton's laws of motion, then the position of a stone that's thrown upward at 64 feet per second from a bridge that's 96 feet above a river follows this particular position function. Once we get to, well, let me say it this way. At time 0, we would have a height of 96. Therefore, this rock is starting 96 feet above the river. But when S ends up equaling 0, that means that the rock has actually struck the river. So the position is all calculated relative to the river, not the bridge. So part A, find the velocity and acceleration functions. Well, this would be easy if you remembered or recognized that velocity and acceleration are simply derivatives of one another. So while the position function s is given to us, the derivative of position is velocity, and the second derivative of position, which happens to be the first derivative of velocity, is equal to acceleration. So if you hadn't seen that yet, and this might be the first time, well, now you know the relationship between position, velocity, and acceleration, and hopefully that makes sense. The rates, I should say the units, adjust because each derivative represents a new rate. While the unit in part A, the original function, the unit is measured in feet, our second unit would be feet per second because we have the y-axis and the x-axis combined into a single unit. And then finally, again, if we had a graph of velocity, then feet per second ends up being our new unit. And sometimes we call this feet per second squared. If you've had some sort of physics class, perhaps you've seen this notation before, not really understood where it came from, and where it comes from is precisely this. It's the derivative of a derivative. And so when we combine those two units, feet per second, well, now we've got feet per second squared. For question B, when does or what is the highest point above the river reached by the stone? Well, let's remind ourselves that the highest point occurs when the upward movement stops and begins to fall. So this happens when our velocity is equal to 0. So by setting the velocity function or the derivative of position equal to 0, we find that the rock will reach its highest point at 2 seconds into its flight. And according to the graphs over here, to save ourselves from calculating this, then 160 feet is the highest position. So after 2 seconds, the rock reaches 160 feet above the river. And question C actually has a couple parts to it. With what velocity will the stone strike the river? Well, first off, we need to know when the rock will hit the river, when the stone strikes the river. And that happens when the position is equal to 0. So when we substitute I'm sorry, when we try to solve this equation, when does 0 equal negative 16t squared plus 64t plus 96? We quickly find that this is a quadratic that's not factorable. And if the quadratic is not factorable, then I think the quadratic formula would be a good use at this point. So when well, we could factor out the negative 16 like I've done here, and then use an a value of 1, a b value of negative 4, and a c value of negative 6. That makes our quadratic formula a little bit easier to work with. The quadratic formula produced two answers, 5.16 seconds and negative 1.16 seconds. We can't really have a time of negative 1.16, so I've crossed it out and called it an extraneous solution. So that tells me that at time 5.16, that's when the stone strikes the water. But the question is asking with what velocity does the stone strike the water? So I'm going to take this t value, time of 5.16, and I'm going to substitute it into my velocity function. And when I substitute 5.16 into this velocity function, negative 32t plus 64, then we see that the stone struck the river at 101.19 feet per second. So lots of things going on there with this particular example. Computing the derivatives wasn't all that challenging, but interpreting the derivatives and recognizing what they mean is pretty important. One thing I do want to point out before we move on, this a of t, this acceleration, is a constant here. And perhaps you've heard that before also in your science classes, that the rate of acceleration is constant on Earth. And that's exactly what our math here shows. The second derivative of the position function is simply negative 32, and that's what we call our gravitational constant. The gravitational constant on Earth is negative 32 feet per second squared, and that's approximately negative 9.8 meters per second squared if we're using the metric units. Now, the story goes that Isaac Newton really established calculus to describe physical motion or mechanics in the real world. But as it turns out, calculus is a wonderful tool to analyze business models as well. And so if we take these definitions and apply some calculus concepts to them, things become pretty helpful and reasonable for us. So C of x represents a cost function, and it tells us how much it costs to produce X number of items in some sort of manufacturing process. So there are all types of costs that go into manufacturing goods, not only the material cost, but the labor cost and the capital cost for the equipment and building space and so on. So all of those costs rolled together, there are functions that can be used to establish how much it would cost to produce X number of items. It's often helpful for us to figure out what the average cost to produce some items are, because you can imagine that if you spend all of your money up front gathering employees and building a building to hold your manufacturing process, to build just one item, it's going to be awfully expensive for one item. But as the number of items increase, the average cost tends to fall, and that would help us determine what an appropriate cost for selling our goods would be. But anyway, this average cost formula, sometimes called C bar because of the bar on top of C, is simply the cost function divided by X. Now, the marginal cost is indicated by our derivative notation, and that should make sense when we describe the marginal cost is the cost to produce one additional item after producing X items. So in other words, what's the rate of change at X? How much is the cost changing after we produce X number of items? So question A simply asks us to determine the average and marginal cost functions based on. And so our average cost, of course, is our cost function divided by X. We could leave it like that, but what I ended up doing was I divided all three of these terms by X, just to make it a little bit more perhaps appealing. So we don't have this giant fraction, we just have one fraction at the end. So this 0.02x squared divided by x gives me the negative 0.02x. 50x divided by x is 50, and 100 divided by x as well, just 100 over x. Now the marginal cost function would be the derivative of this guy. So 2 times negative 0.02 is negative 0.04. And then we've got 50, the constant here. So we've got our marginal cost function as well. So a lot of times in economics or in this kind of business calculus, if you will, um, the items that we're producing, we don't really have a name for these items, and rather than calling them items, you'll hear some instructors call these widgets, just things that are being made. And so now that we have the average and marginal cost function, let's determine what the average and marginal cost is when you only make 100 items or 100 of these widgets. Well, when we substitute 100 into the cost function, the average cost function, we ended up getting $49 per unit. And so the total cost is going to be $4,900. And when we divide that by 100, we get $49 per unit to produce 100 of these widgets or 100 of these items. Now, what's interesting is if I find the derivative of the cost function at 100, well, then I see that it only costs $46 to create or to produce that next item. And if the average cost is $49 per unit, and to make one more, it's only going to cost $46, well, you can see the intrigue here. You can see the motivation for the person running the business. Well, go ahead and produce one more because it costs less to produce that next one than it has cost on average so far. Similarly, and perhaps in a more obvious notion here, the average cost to produce 900 of these items is $32.11. So it's much cheaper on average once we're producing 900 of these items. And then the derivative at 900, the derivative of the cost function, ends up being $14. So to produce that next item beyond the 900 that only costs $14, and you're definitely saving a lot of money at that point. And those cost savings, while it definitely costs a lot of money to produce 900 of these items, at least for each item individually, the average cost is going down. And we call that economies of scale. When you start producing more and more items, it becomes cheaper to produce each item individually. The total cost is still pretty high. In neither of these cases did we calculate the individual cost directly, but the marginal cost and the average cost per unit is continuing to drop. In other words, it becomes more affordable per unit, not total cost, but more affordable per unit when many units are being produced. Again, we call this economies of scale. Well, I hope you enjoyed this discussion, and I hope that it opens your eyes to some applications of calculus. Some of it's pretty obvious and straightforward. Others may be a little bit unusual for you to learn about this first time. But if you have any questions with what was presented in this video, please make sure that you reach out to me and we can chat about it when we see each other next time. Thanks for watching.